students. So this is Springs part 3, and in this video we will discuss some of the numerical problems from the chapter of springs. We will start with the simple questions and then we will move forward. So let's see the statement. A compression coil spring made of an alloy steel is having following specifications. Mean diameter of the coil, capital D. It is 50 mm. Wire diameter, which is small d, 5 mm. Number of active coils 20. If this spring is subjected to axial load of 500 Newton, calculate the maximum shear stress. Neglect curvature effect. Now in the question it is given that you have to neglect the curvature effect to which the spring material is subjected. So we are writing the given data. Diameter of the coil, capital D 50, small d, wire dia 5, number of turns 20, and load 500 Newton. And you have to calculate shear stress. So apply the formula for shear stress, Ks 8 WD by pi d cube, and Ks is the shear stress factor, and it is given as 1 plus 1 by 2c. So c is spring index. Spring index is calculated as capital D by small d, and it is 10. So from spring index we will calculate shear stress factor 1 plus 1 by 2c, and it is 1.05. So shear stress will be Ks 8 WD by pi d cube. Put the values and you will get the answer 534.7 megapascal. Second question, a helical spring is made from a wire of 6 mm diameter, wire dia small d, 6 mm, and has outside dia. So outside dia is given, not the mean dia. Outside coil dia is 75. If the permissible shear stress is 350, modulus of rigidity 84, find axial load which the spring can carry and the deflection per active turn. So you have to find the axial load and deflection. First write the given data. Small d wire dia 6, outside dia 75, shear stress 350, modulus of rigidity 84 kilonewton. So we have converted into Newton. So first of all, the first step will be to calculate mean diameter of the spring, which is outside dia minus wire dia. As you can see in this diagram, mean diameter is D. Outside dia will be DO. If we subtract this radius and this radius, means we subtract the diameter of wire from the outside dia, you will get the mean dia. So mean dia will be D outer minus D. So 75 minus 6, 69 will be the mean dia. So we will find the spring index to calculate Ks D by D. It is 11.5, and we need to find W axial load and deflection delta per active turn. Neglecting the curvature effect. So first of all, we will solve the numerical by neglecting the curvature effect, and we will consider the shear stress factor Ks 1 plus 1 by 2c. We calculated 1.043, and we apply the formula for shear stress. Tau is equal to Ks 8 WD by pi d cube. Put the values and you will get the W 412.7 Newton answer. Similarly, you need to find the deflection, apply the formula for deflection. These formulas we have derived in the previous video, 8WD cube N by GD4. So from this formula, you need to calculate delta by N, and you have to put the values of W, D, G, and D. So your answer will be 9.96. Now the same question we will do by considering the effect of curvature. So instead of using Ks shear stress factor, we will use wall factor, because when we have to consider the curvature effect, then we will use wall factor. So wall factor is 4c minus 1 by 4c minus 4 plus 0.615 by C. So put the values of C and you will get wall factor K 1.123. Now shear stress, apply the formula K AWC by pi d square. So put the values and you will get the value of W. Similarly, for the deflection, you apply the formula, put the values, and your deflection will be 9.26. Third question, design a spring for balance to measure 0 to 1000 Newton over a scale of length 80 mm. The spring is to be enclosed in a casing of 25 mm dia. Approximate number of turns is 30. Modulus of rigidity is 85 kilonewton per square mm. Also calculate maximum shear stress induced. So we will write the given data. First of all, load from 0 to 1000, that is maximum load is 1000, deflection is 80, number of turns is 30, and modulus of rigidity given to us. Now how we will design the spring. So as you know, since the spring is to be enclosed in a casing of 25 mm diameter, therefore outside dia of the spring coil should be less than 25. Okay. So since in our question it is given that we have to put this spring in the casing which is of 25 mm diameter. So it is obvious that our spring should be less than 25 mm diameter, means its outside dia should be less than 25. So outside dia is DO, that is mean dia plus wire dia, D plus D. We know that deflection of the spring, apply the formula 80, that is deflection given to us 8 WC cube N by GD. We put the values that we are given to us. C is not given to us, D is not given to us, so we will get this relation C cube by D is equal to 28.3. So now we have to hit and trial. We assume that the small d is equal to 4 mm. So from this value we will calculate the value of C 4.84 and capital D we have calculated 19.36. These are hit and trial values, means we are not sure that this answer is correct or not. How we will check? We will calculate the outside diameter of the spring coil. D outer is equal to D plus D, that is 19.36 plus 4, and outside dia comes out to be 23.36. So outside dia is 23.36, which is less than 25. Means you can put this spring in the casing. So it means that your wire dia, the assumed dimension D is equal to 4 is correct. Now how will you calculate the shear stress? We have to apply the formula for shear stress K 8 WC by pi d square, and the value of wall factor is 4C minus 1 by 4C minus 4 plus 0.615 upon C. So put the values of spring index C and you will get the wall factor 1.322. So put the values in the formula for the shear stress and you will get your answer. So in this question, basically we have to first assume the answer and then check whether it is right or not. So in this case, we have assumed wire dia 4 mm and outside dia comes out to 23.3. So it is less than 25. So we can say that this design is correct. Maybe other different person select some different dia. So the answers could be vary, but the method should be correct. Okay guys, rest of the things we will discuss in the next video. Thank you.